True. Okay, so we're on to thermodynamics. The first part of thermodynamics is involving temperature and ideal gas. All right. Um, so that's where we are at right now. The first thing about this is it's about calculating the pressure of a gas. Now, in secondary school, we talk about how gas can exert pressure. Even though gas is not a liquid, it's not solid, you know, it's something that if you just swipe your hand across the air, it feels like there's nothing. But if you put gas like in a container in a balloon, for example, it can exert pressure. So in secondary school, we talk about how gas can exert pressure. So you have things like frequency of collision, um, exerts a force, a pressure on the wall. But what about the quantitative side? What about the numbers? Can we actually calculate it out? To calculate the numbers, you will need to know the algebra of it. And that's what this question is about. Because if you know the algebra of it, then you can calculate the numbers later on. It's just about substituting variables inside. So let's take a look at this. Hopefully you can get the answer if you have tried. Um, if you collide, if you start going towards the right of the wall with a speed, a velocity u, and you collide, and it's an elastic collision, which tells you that momentum is conserved, you should get minus mu because you'll be bouncing off towards the other side. So it will be like this. The time between collisions with the same wall. So imagine that you, um, if you collide, you went to here, if you travel to here, and then you collide, and you go back to that same wall. So it's L and L. So it'd be 2L over U. How do we get that? Speed equals to distance over time. Time equals to distance over speed. So it's 2L over U. Number of collisions with this wall per unit time. Unit time is 1 second. So if you take uh the so this is the time. If you take 1 second over the time taken to collide, then you will get the answer, which is 1 over 2L over U, which is L over 2U. So this will be L over 2U because this is per unit time. If you take a certain amount of time to travel to hit the wall, how many times can you hit the wall per second? So that's known as the number of collisions with this wall. All right. So the rate of collision, rate of change of momentum is then what you have. This is the change. It will be defined as the change in momentum over the time taken to collide again. So you will get minus mu minus mu over 2L over U. You should get minus 2mu over 2L over U. So what would that be? Minus mu squared over L. Okay. Um, so this is what you'll be experiencing, rate of change of momentum of the molecule before and after. This is actually the force. So you should put this down, minus mu squared over L. This is actually the force that the molecule experiences. If this is the force that the molecule experiences, then the force on the wall is the opposite, which will then give you mu square over L. Newton's third law. So I repeat, if this is a force that the molecule experience, rate of change of momentum is, it will be the force the molecule experience in order to have this change in momentum. Then the force experienced by the wall, acting on the wall, would simply be the opposite direction. So in terms of diagram, figuratively, you should be looking at something like this. If you experience, if the molecule experiences a force in this direction, which is mu squared over L. So this is on the molecule. Then the wall should also have mu squared over L. So these two are the same except for the sign that is different. Moving on. So for this one, when you're talking about pressure, so this everything here, because of the force over the area, you get the pressure. Okay, everything that is derived here is based on this. If you refer to the notes, there's actually like whole long stretch of derivation on that you're not required to memorize, but you're required to study. So because of this formula being derived from this, and because of the elastic collision, so the type of collision between gas molecules must be elastic. So actually, the answer for this one can be found here. Now, what if it's not elastic? If it's not elastic, then you can't get this answer. If it's not elastic, then you have to account for the decrease in kinetic energy over time because of non-elastic collisions, and the speed will decrease over time. But ideal gas, this is all based on ideal gas, so the collisions are all elastic, to simplify it. Okay? So for this one, in practice, gas molecules will collide with one another. Here's the thing. If K, using answer in BI, which is this one. So if collisions are elastic, all gas molecules would travel the same speed. So pressure, as you can see here, depends on this speed. And this speed, you're taking the average. So it doesn't matter if you have collisions, because the collisions would, whether you, the collisions that you have would allow the gas molecules, because it's elastic, so it allows the gas molecules to have the same speed, and therefore you have the same pressure. So the pressure is not impacted by the collisions. So pressure would still be the same after counting for collisions. Okay. Show that the average kinetic energy of an ideal gas molecule. So for this one, you have to go back to this expression. Okay. So you have to get kinetic energy out. So what you do here is taking note that kinetic energy is half mc squared. Okay. Then what you can do is try to make this into this. This should be the big M. This is the number of particles. This is the mass of each individual molecule or each particle. So you can express it to a big M, which is defined as the total mass of the gas, and then multiply by half. Over here. And then you can bring the 1/3 over, which will become 3. And then you get 3/2 PV, which is also equal to 3/2 NKT. So it tells you that the KE is proportional, directly proportional to the temperature for this case. And that's how you solve for this question. All right. So for the next one, you have this ideal gas, first law of thermodynamics, take note of the direction. First thing you want to take note is that this is expansion. So we talked about this last week. If it's an expansion, this must be a negative. Okay, so doing the question, shade in figure 2.2, the area that represents heat exchange between gas and surroundings. If you start with this, and they already tell you that delta U is 0, so the heat exchange is then the negative of the work done, which is then, in this case, area under graph for this one. So why do we do with volume? It's because it's integration pressure with respect to volume. So you have to shade touching the volume axis. Work done is by definition this. So you got to integrate with respect to the volume. All right. If the change in volume takes place, okay, if it takes place slowly, you have, do take note that it means you have no change in KE. The reason being is because if you push something very slowly, then that thing itself will just be slowly nudged by you. It doesn't change the KE very much. All right. If you push it very fast, quick change would mean an adiabatic process, which will indicate that the volume takes place, which will indicate that the Q in the heat exchange is 0. Because the idea behind it is, if you do it fast, the heat will have no time to change because it's too fast. Okay, but this will cause the KE to change. So how will the KE change? So going back to ideal gas, so delta U increase is equals to Q in plus W on. Make sure you keep all the directions there. This is increase in internal energy. This is heat supplied to the system, work done on the system. If this is 0, then you have this, and this is negative. So, which means that this will be negative as well. If your delta U is negative, then your temperature will drop. And that means your speed decreases. So that'll be the answer for this. Now, this is very interesting. This is the reason why we have air cons working. Basically, if you expand very fast in the aircon, then you're going to lose a lot of if you expand very fast, then your temperature will drop over here due to the first law of thermodynamics. So this will cause the air to be colder. Okay. So moving forward, using kinetic energy. PQ. So this one is about pressure. You got P equals H rho G. Um, this is kinetic theory, so you don't really use that. So what you can do is got to, this is basically secondary school stuff lah. Temperature increase, that means K increase, then frequency of collision increase, then pressure increase. So yeah. And the temperature of R remains unchanged and the volume decrease slightly. So this one, if volume decrease, number of particles per unit volume decrease, that would mean frequency of collision will increase. Basically, if the space become lesser, you will hit the wall more often. Because if you bounce back and then you go hit again, if the space between two walls get lesser over time, you keep hitting the wall even more. Then pressure would increase. So these are good 2 marks to have. All right. um, I hope you've tried this first. I think I would like for you to try this before you go through it. So it's 1 hydrogen atom per cm cube. So its volume is 1 cm cube. N is 1. Temperature is 3.5 K. Mass is 1 U. So U is a unified mass constant. Check your data sheet for that. So you can actually use PV. Okay, start with this. We should give you 302. You have the NK delta T, NKT. So you can, this is 1, this is K, you can find from data sheet, this is 3.5 K, 3.5 Kelvin, 1/3, N is 1. Mass is over here, you can find this. C is what you need to find. Pressure exerted can be found, PV equals to NKT, V is 1. So it can be found. This one is first law lah. Sum of the heat supply. Hey, no, it's not first law. This is sum of KE plus PE. Yeah. Increases in speed. Okay. Your answer should be no, in case you're wondering. The thing is because internal energy is about internally. What you have here is bulk. It's bulk KE that will increase. All right. So the bulk KE can increase, but the internal energy will not increase because you're looking at internal KE. Each of them, the average speed of the molecules with respect to each other will still be the same, even though the gas has increased in speed. But inside, everyone increases with the same amount of speed. Relative to each other, there's no increase in speed. So there will not be an increase in frequency of collision. There will not, so that the internal energy is still remain the same. Okay. So there's a difference between internal energy and external energy. External energy is like those half mv square and mgh and those things. Internal energy is like uh average kinetic energy, average speed of gases, gas molecules. So they will not affect each other. Okay. Using ideal gas equation. So use this and the fact that this A, get the volume out. And you got L1. Okay. When thermal equilibrium is established, the temperature will be the same. Okay. Um, so you will get this one. We don't include K because K is a constant. So it will be cancelled out. So you can use this to find the ratio because V is L1 times A. This one is L2 times A. So you can find the ratio from there. N is mass over MR. So you got nitrogen and you got helium. Nitrogen, I think, is 28, 28.4 times Avogadro's constant. So plug that in and find for this one. Okay. Okay. So for the next one, we have pressure gas thermometers. Okay, so what they do is that it's basically a manometer lah. So you have like a gas here, then it goes into a tube like so. So this is that gas, and then you have liquid in the tube. So the pressure can be found here, P equals to H rho G, where H is the difference between the levels. All right. The volume is constant. Oh, in this case, volume is not constant. Oh, then they'll be using a piston in that case. Yeah, replace this with a piston. So that can work as well. Either that or they use different volumes so they change the V here to obtain that sort of pressure that they want. Or you can use a piston to adjust that volume. Regardless, when you see a question that involves gas, and then you got pressure, volume, temperature, all right, you would then have to think about PV equals to NKT, and then you can apply this. So because PV over T equals to NK, if you are using the same gas, the NK becomes a constant. So you can use P1 V1 over T1 equals P2 V2 over T2. And taking note that triple point of water is 0.16 degrees Celsius or 273.16 Kelvin. Take note that everything here must be in Kelvin for this equation to work because it's all SI units. All right, then you can find T1 from here. Over here, they realize, hey, these are not consistent. So the only reason, if you have inconsistent temperature, it will mean that it's not ideal gas. Like what I mentioned earlier, if it's not ideal gas, the collisions cannot be elastic. That changes the pressure readings and things like that. And also it affects the T. Okay. Since none of the gases are ideal, how can we find the true value of T? Well, they mentioned a T versus P graph. So you can draw that out first. So if you draw this out, right? And if you take different readings, okay, and plot it out, you'll get the real T here. Because a real T, when the pressure is zero, this is ideal gas. When the pressure is zero. So when the pressure is zero, right, you get a real T. And that will be the true value of T. So you can have different pressure. You can have like 100,000, uh, 90,000 over here. You can use all of these values that you have. 150 and 10. So you can have like 100,000, then you can have like 50,000, you have 10,000. So an ideal gas would give you a fairly constant value lah. But in this case, uh, if the when you reach here, that would be ideal gas. So you can have real gas giving you different temperature, but if you extrapolate, you can actually get the true temperature. Um, this one, try first, then we'll talk about it. I would say per hour is 60 minutes. You can use MLV, latent heat of vaporization. That's Q. This is work done over time, Q over T. 15% use that, and you can find this answer quite easily. Over here, again, to maintain the original pressure of 220. Oh, so you have different temperature, convert to Kelvin. Otherwise, you won't get answer. Use P1 V1 T1 equals to P2 V2. You can get a fraction. Let's see. You got to assume that V is constant. You got to increase. Oh, no. You can't use this one. You can't use this one. You got to change a bit. PV equals to NKT. V is a constant. So it's P over N1 T equals to, so I'm using P over NK T, P over NT equals to K over V, which is a constant. So you got to assume the tire is a constant volume because it's a tire. Then you can find a fraction from there. But it's a fraction of air that must be removed lah. So you got to do a bit of minusing off after that. Once you found a fraction, you got to minus off. What happened? What are you looking at? Are you okay with that circular motion question? Yeah. Okay. Um, This one you got to use the PV equals to 1/3 Nm. In a silk tire is double or is one is constant. So it's a silk tire now. Yeah. So use this to go and find. You should be getting a square root of something because your C here bring over becomes a square root. So don't forget to use that. This one definition determine number of molecules in gas A. You have this, so PV equals to NKT. N stands for number of molecules. Mean translation energy, which is 3/2 NKT. So you can use that. In case you're wondering how do I get this, is the conversion earlier that we've made, which is this one. This one. This is KE. Yeah, over here. So take a look at this one again. So we're done with this. Change in internal energy. So you'll be using 3/2. Delta U is then, if U is 3/2 NKT, then delta U is 3/2 NK delta T. Okay? Work done is Q in delta U increase equals to Q in plus W on. So always check for Q in. Oh, it's insulated. So there's no Q in. There is no Q in. So this is 0. Then that's why it's a warm-up question. So it's just take whatever answer you have here, put it here. That's all. Try this first, then we talk about it. Okay, we're done for this. Hope you get well soon. I'll see you again next week, hopefully, and then we can go through the questions if you have questions. I'll send you the answers as well. All right, take care. Goodbye.